Okay, next speaker is from Indonesia. Is that right?
Yeah.
Mr. Sunasa. He's going to speak about non-contact debonding identifications.
So good afternoon, ladies and gentlemen. Let me introduce myself. So my name is Timotheus Yonatan Sunarsa. I come from Indonesia, and currently I'm studying in KAIS as a master candidate under the guidance of Professor Sun. So today I'm going to present my research in debonding identifications, which is non-contact debonding identifications in adhesive joint using guided waves. So yeah, the outline will consist of like the motivations and then the proposed method and also the experimental validations, and the last is conclusions. So let's start in motivations. So for me, I'm going to discuss about debonding identifications, and the debonding problem is actually related with the adhesives. In the ancient times, actually, people already use a lot of adhesives, like in Egypt and Romans. They kind of extract the adhesive from the birchwood and then from animal glue. And then in my country, like we have the biggest Buddhist temples. It's just like Borobudur Temple. And then like it consists of like rock structures. And then in the ancient times, they kind of stick the rock structures between like rock and rock using adhesives, which is animal glue and also egg. So, and then jump to the modern times. This adhesive is actually widely used in the aeronautics and automobile industry, since this adhesives give some benefits, for example like lightweight and high strength and also corrosive resistance. But then, it's also like works for complex structures, which is kind of hard for a bolt when you stick it with a bolt. But then they have like some kind of problems. The problem is here about the bonding quality. Like you can see here from these pictures, like for a good bonding, you can see that the blue color there is representing the adhesive. So with a good bonding, there will be like fully bonded between specimens. But then when the bad bonding happens, so for example, like there is a void or debonding sections, this kind of like causing some decrement in the power and strength. So then, as we know that the industry that use adhesive a lot is in the aeronautics and automobile, which is they like really high in like lifetime. So like people always use it over time. So then like the good bonding is really needed here. So then like during the fabrications, we need to have like some good inspections. So then, me and my professors, we decided to propose a laser ultrasonic scanning systems to evaluate the debonding problem, the bonding conditions. So first of all, I'll talk about the fully non-contact laser scanning systems. So this is the schematic of the laser scanning system, which is consisting of excitation units, sensing unit, and also the data acquisition systems. Like in our lab, we use for the excitations of the ultrasonic wave, we use laser ultrasonic ND-arc laser. And then since our ND-arc laser is a fixed laser, so then we need to move the points by using galvanometer, so that we can control the laser into the interested point. And also to sense these ultrasonics, we use laser Doppler vibrometer made by Polytech, because they have like good quality. And I think a lot of scholars, they also use LDV as their reference. And this one is the basic principles of laser Doppler vibrometer. So this device is measuring the shifting frequency, so that we can know the velocity difference, like velocity changing in the specimens. And then some working principle about the ND-arc pulse laser here is like, so when the ND-arc laser shoots the lasers, it has some thermal it will cause some thermoelastic expansion in the specimen, so then that these thermoelastics will generate some ultrasonics, which is later we can sense it with the laser Doppler vibrometer. We give you one good example here from, so this is demonstration. So when the laser ND-up and the galvanometer is excites in one point, and then the laser Doppler vibrometer is moving each points, getting a sensing, and then like later on we can visualize how the wave propagates in the specimens. So you can see like that's the wave propagations in the specimens is really clear. I think this one is from intact specimens. So then later on, you can see here like from the wave propagations we have two comparisons. The first one is from intact cases, and the second one is from the damaged cases. So you see from the wave propagations, and then we extract it into the energy propagations from the amplitude difference. We can tell like in the intact cases there is nothing happening in the energy propagations, and in the damaged cases you see in the middle there is like one higher energy. And then by using a signal processing, we could process this one, and then like we could visualize the hidden notch. But I called that one as a conventional scanning because you fix one laser and then you move the other laser. The problem here is like the scanning area will be limited, since like, so there is a problem with the ND-up pulse lasers. The first problem is like it causing some thermoelastic expansions. When the thermoelastic is too huge, the energy is too huge, it can cause an ablation in the specimens. And usually like for aeronautics or automobiles, it's really sensitive to like aesthetics. So when so if there is ablation happening in the specimens, like the client will not like it. So then we should carefully set the energy, and then this can causing like the energy problem. So then like, because as you see like in the upper part, the distance is different with the bottom part. So then because the distance is variance, it's also need like several number of that time averaging, which is like in the conventional we usually our averaging time is 200 times. So then to overcome this kind of problem, we propose a new schematic that is a synchronized laser ultrasonic scanning strategy. So what's the difference? Here the difference is like we move the excitations and the sensings synchronously together. So by moving it together, we will have a fixed distance between excitations and the sensings. So then we can have larger scanning area, since we just need to move all the lasers. And then we could reduce the averaging times, since it's dependent on the distance of the wave propagations. And also one good benefit is also like we can do like spatial comparisons between each other. But by using this synchronized scanning, it's kind of different, because in the previous stage, in the previous scheme, we could like make a wave propagations video. But then with this synchronized laser ultrasonic scanning, we couldn't make the wave propagations because it's based on spatial points. So we should make a damage in the extraction and damage detection by spatial comparisons. So the main features that I use in this experiment and for this scheme is like you excite the point and the wave propagation sensed by the sensing laser. So we have the wave propagation distance, and then in between them we call it a spatial point. And here, to make like some kind of spatial comparisons, there might be some overlapping between the wave propagation distance caused by the excitation point and the sensing points. And then, so if the condition is if the scan gap is usually smaller, like if you want to make high density sensings, you make the scan gap, you decrease the scan gap. But if you want like lower intensity, you can increase the scan gap. So if the scan gap is still overlapping, between the spatial point is overlapping with the wave propagation distance, we assume here that the spatial points will have some influence to the previous points, so that it will put some weight to the observed point, and then from the observed points to extract some damage index, we try to analyze from the energy. And then if there is no overlapping sections, it will have no weight points. And then finally, we could have a baseline free damage localizations. And let's see the experimental validations. So here is the experimental setup. Like the setup is consisting as the device I mentioned before, laser double fiberometer, galvanometer, and DF laser. And the distance is about 1 meter from the specimens to the devices, the scanning systems. And here our specimens is bonded aluminum sheets with adhesive. So we have two kinds of specimens. The first one, the specimens called as AL1. It has a big bonding in the middle of the specimens, and the second one is AL3, which is have like just debonding in the middle part of the specimens. In this experiments, we use averaging 50 times, and then the total scanning point is 64. Like here, the scanning area is still small because the specimens is not that big, and I use like vertical direction, so then it has some problems. So then this is the result. So from the raw time domain signal, you can clearly see that the difference between the intact and debonding is really huge. So when the laser hit the debonding part, it has higher energy, and when the laser hit the bonded specimens, it has lower energy. And then from here, we could extract it as a normalized damage index. So then, by putting it to the algorithm I explained before, we could visualize the damage. Like in the AL1, we can clearly see that the damage occurred in the middle, and AL3 also we can see some difference. But then like you can see like some blue color here. It's because of like in the middle it put like some weight, so then the color is still blue. Like for now, since it's a preliminary sections, so then we haven't like jumped into like how big and how big the debonding part is, but then we can clearly see that it's showing like a good point here to jump. So at the end, yeah, the summary here, like our damage detection technique using a fully non-contact laser ultrasonic scanning system and synchronized scanning strategy is developed and successfully detect the eliminations for these specimens. And yeah, we use the energy of the wave propagations as a damage sensitive feature here, and then it's working properly. But then there is still some limitations here, like spatial surface treatment need to be implemented since it's a laser. And then with current scanning strategy, the scanning area for this specific specimen is still also limited. So later on, we will try to move, like maybe try in the horizontal and then try with another specimens as well. And then to overcome the first problem, we also trying to work with another ultrasonics devices like air coupled transducers. Thank you for your attention. Is there any questions and discussions?